Hello and welcome to this demo. Today we will be flattening a textured chair for flattening and rendering with ExactFlat for Rhino and ExactFlat Monarch. This file has already been flattened, so we're looking at the 3D reference model right here. And if I turn on our pattern layer, we can see the 2D pattern. So we've already flattened this chair, but we'll be deleting the flat patterns and we'll be going through all the steps required to create a mesh from the surface to texturing to flattening this chair again. So this is what the final result looks like. We've already flattened it, and if I turn back on our notch highlights, we can see we've added notches all the way along the pattern, and all the work's already been done here. So this is what the final result looks like. So now what we're going to do is we're going to use ExactFlat. We're going to click the broom icon, and we're going to delete the flat pattern. We're going to undo all the work of flattening, and we're going to delete the flat pattern. We're going to go through all the steps to create the mesh and to flatten it all over again. So what we're going to do first is we're not going to delete the textured mesh layer. We have this model textured for us after we created the mesh and everything, so we're not going to delete this, and we're going to keep our piece boundaries. This layer here, I just have curves on here that show the division or boundary of the different pattern pieces. So we're not going to delete this layer either. We're going to keep this as a reference, but what we are going to do is we're going to go back to our mesh layer and our remesh layer, and we're going to delete the meshes on here, and we're going to repeat these steps to reflatten this file. So we're just going to select our meshes here. We've got 14 meshes selected. We're just going to press delete to delete these meshes. So we'll go back to our surface layer here. At this point, we're in rendered viewport right now. This is so we can see the texture of the mesh, but what we're going to do is we're going to click the down arrow, and we're just going to go to shaded viewport. This is a little easier to work with. We get a bit of a higher frame rate, so the controls are a little more responsive. Plus, we can see more of the contours and topology of the surface or mesh here, because we're not viewing a smooth shaded model. The ISO lines of the surface make it a lot easier to see the curvature and to see the boundaries. So we start with a surface, and the surface could come from any CAD package or any source. It could come from someone who's modeled it for you. It could come from a different CAD package such as SolidWorks or CATIA, NX, Inventor. So long as you can bring the surface data into Rhino 3D, the source of the model does not matter. So long as we have surface data or mesh data, ExactFlat can work with it. So in this case, we have surface data, and we're going to go ahead and we're going to first start. I don't recall if this came in as a single poly surface or if it came in as separate surfaces. Either way, the first step we're going to do is we're going to join it all together. So right now we've got one poly surface. I'm going to go ahead, I'll explode it into 123 surfaces. So if this is the case, if you have multiple surfaces, the first step is always going to be to simply rectangle select everything and just join this together. So we're joining 123 surfaces into one open poly surface. And the reason we do this is when we go to create a mesh, if we create a mesh out of a single poly surface, the boundaries between individual surfaces, the mesh is coincident along that boundary. So if we mesh all the 123 surfaces separately, we might have mesh boundaries that don't line up, or the meshes aren't aligned. But if we mesh a poly surface, then all the separate meshes for each individual surface, they're all aligned. So what we're going to do now, we're going to go ahead and we're going to create a mesh. And to do this, we just use the Rhino mesh command. So we can either type in the command on the keyboard, or we can use the button. I think it's this one right here. So we can just create a mesh. For a surface, for simple surfaces, what we can do is we can go to simple controls, and usually if you just drag the slider all the way over to more polygons, we can usually get a decent mesh. But because we've got a mix of developable surfaces, planar surfaces, and high curvature surfaces here, we don't get the best mesh from the simple controls. So if we just use the cell mesh command, we can select the mesh and we can get a bit of an idea for what it looks like. And we can see we've got the colors really aren't bad here. I'm going to change my display color to black. This is going to allow me to see the mesh a little better. So we've still got the ugly yellow of the chair contrasting, but we can see we've got some fairly high aspect ratio quads back here, high aspect ratio triangles, and over here it's even worse. So this mesh is not a good mesh. We're definitely going to have to use the Remesher on it, but we can get an even better starting mesh out of Rhino. So what I'm going to do is sell mesh once again. I'm going to delete that mesh and we're going to create a new mesh. So instead of using the simple controls for this one, what I'm going to do is we're going to hop over to detail control, and I'm just moving the mouse slightly across the surface here to get an idea for the scale of the model. We know this was modeled in millimeters, and as we move our mouse we can see that the units are changing quite rapidly. So what I want to do is I'm trying to get a sense for how big I want my quads, and what I'm going to do is I'm going to start off with a maximum edge length of, we'll start high. We're going to start with 50 millimeters, and we're going to do a minimum edge length of say 5 millimeters. I usually do about 1/10 of the maximum, and I set my maximum aspect ratio to 2. That means that I want my longest edge to be at most twice the length of my shortest edge. And we're going to hit preview, and we're just going to see what kind of mesh we get here. So meshing is going to take a little longer because we're meshing 123 surfaces, and we're hopefully getting some better fidelity out of them. So we can see that instead of having very elongate quads, we're starting to see meshes here. It's hard to tell because of the yellow coloring, but we're starting to see more squares. So we're eliminating those very, very long high aspect ratio triangles, and we're eliminating the very, very long quads. We're also helping to ensure that we have a more uniform size and distribution of the triangles. We're still going to be using the adaptive remesher for this, but by ensuring a more uniform distribution of triangles going into the adaptive remesher, we're going to get a better result. I still don't like how big a lot of these triangles are, so I'm going to reduce this a little further. So we're going to say about 30 and 3 for our maximum and minimum edge length, and we're going to hit preview again. So our first time we ended up with about 189,000 polygons, and this time we've got about 197. So we've increased the polygon count slightly here, and we're looking better. I'm just going to reduce this again further, so we'll do 20 and 2, and I'm just trying to get a fairly good sampling as input for the adaptive remesher. So this is looking a lot better. I like the way our mesh looks here, so I'm going to go ahead and click OK, and as usual, sell mesh, and we're going to put this on our mesh layer, and we'll turn off the surface. So yellow makes it very difficult to see the tessellation, so we'll change the color to black or by layer. So now we can see our input mesh here. We've got fairly consistent sizing for our quads and triangles all the way across. So now what we're going to do, we can't flatten this as a single piece, so we're going to explode our mesh. And now we've exploded it into 123 meshes. It's quite a few pieces to work with, but this is the best way to ensure that we get the kind of results that we want. So we do have our piece boundaries layer here. This was done earlier, and this just allows us to view the boundaries of the pieces. So we can select all the meshes up to these boundaries and know that we're selecting the right pieces here. So it's not the most intuitive way of doing it, unfortunately, but it's the best that we have. So we're just going to start selecting meshes here. So holding shift on the keyboard, we're going to shift and select and join together all of these meshes here until we've selected all the meshes that belong to this pattern piece. So we've got all our meshes selected for the first piece. Now what we're going to do, we're going to click the join button. So we're going to join all these meshes together. And so the way join works is it basically takes, we started off with 18 meshes, so 18 unique collections of vertices and 18 unique collections of faces. We've simply concatenated all those lists together. So what we have is when we start looking at the boundaries between meshes, we've got multiple copies of the same vertex or location in 3D space. We've got multiple copies of that within our single mesh now. So really, these are going to be detected as disjoint meshes. And in fact, if I explode them, what explode does is it looks for unique collections of vertices and faces, and it's going to separate those out into individual meshes. So if I explode this, we can see that we end up with 18 meshes again. So this really isn't the best input for ExactFlat. We don't want those duplicate vertices here. So what we're going to do now is we're going to weld all these vertices together, or remove the duplicate vertices. So we're going to use the Rhino weld command. And what we're going to do is we're just going to use an angular tolerance of 180 as the maximum tolerance. And what this is going to do is it's going to eliminate the duplicate vertices. So we've welded this together now. And if we try to explode it again, we can't explode it into multiple parts because we no longer have the duplicate vertices. We only have one collection of unique vertices in 3D space, and all the faces share that single collection of vertices. So our process after we mesh is we're going to explode our single mesh because we've meshed as a single poly surface. We're going to select all the faces from the mesh that belong together as a single pattern piece. We're going to join them together, and then we're going to weld them. So we're going to repeat this process for the rest of the surfaces on the chair here. To make it a little easier, because I've already processed this piece, I'm just going to go ahead, I'm going to use the Rhino hide command, and I'm going to hide this. This is going to allow me to see the other surfaces here. Also, as I keep meshing, if I see any kind of meshes just kind of hanging out in 3D space here, I'm going to know that I obviously missed a face or a mesh, so it's going to make it easier to detect missing pieces. So we're going to go ahead, we're going to start working on the back here. These pieces are nice and big, it makes it very easy to see and select them. And I'm just looking over here, I don't remember where the boundary is, and it looks like the boundary's right there. So we're at the boundary right here by the looks of it. Yeah, so we're not going to go any further. And we've got this all the way down. We'll make sure that we select the bottom lip. So I'm just going to control and unselect. I want to make sure that we didn't actually have this split in half. I don't think we did. I don't see the red right here anywhere, so I think we're good. We're going to continue on right up to the boundary. And that's something else we can do. If you do decide to use a curve to represent your boundaries, you can simply select the curve too, and that's going to highlight it, make it a little easier to see. So we've got our meshes selected here. So once again, we're going to join, and then we're going to immediately weld with a tolerance of 180 degrees. So now we've got our single mesh, and we're going to go ahead and hide it. So as we start, it's best to work with the biggest, largest pieces first. That way we can get the most triangles, the most clutter out of the way, and it makes it a little easier to see everything else we're working with, and it makes it a lot easier to process the mesh. So we'll continue on with the back part here. See the red right here, so we know this is the boundary. So I'm not going to select anything beyond that. join them together and weld and hide. So we can see here where the curve is going. So we're going to make sure that we select right up to there. Join, weld 180, and lastly we're going to hide that mesh. Repeat the process down here. So from the other side we know that this part is included with the side panel here, so we'll select that first and we'll start our building our piece out from there. And we'll join, weld, and hide. So we're going to select all the curves. This is just going to bring them to the very front, make it a little easier for us to see where they go. So we're just getting a bit of an idea for the layout of the piece. So everything along the front here is one single piece, and then our seat up top here is a single separate piece. So for this chair, when it's manufactured, we don't actually use this front panel as a printed pattern piece. So we're going to omit these pieces here, and instead we're just going to flatten this piece back here. And if we go to our textured mesh here, I believe we textured everything on this, but yeah, so we textured everything, but during production it's cut right here along this boundary, and it's not actually that part's not actually used. But we'll go ahead, we'll flatten everything anyways. So we'll go back to our mesh layer, we're going to turn off our textured mesh, and we'll start selecting our faces. So we'll join, we'll weld, and lastly hide. So at this point, all the remaining meshes should be part of this front piece here. So what we're going to do is we're going to use the cell mesh command. We selected 28 meshes, and just to kind of validate that we haven't forgotten any kind of sliver meshes, what we're going to do is we're going to use the zoom, and we're going to zoom to selected. So it's only created a viewing plane around our selected meshes here. So our last test is to join them all together. And we've joined all the remaining meshes into one open mesh. This is a very good indicator that we don't have any floating, very small floating meshes hanging anywhere that we've missed. So we're going to, now that we've joined them, we're going to weld. And lastly, we're going to hide. So at this point, I can select all the meshes. We should have 0 meshes left, so it should say there are no meshes to select. Cell mesh, no objects added to selection, so we haven't missed any meshes. We've selected and processed every single mesh, joined them together into pattern pieces, and we've hidden them. So at this point, we're going to use the show command to unhide our objects. And now we can see all our mesh selections here. So just to validate that we haven't forgotten to weld anything, we're going to once again cell mesh. We're going to select all our meshes. We're going to switch over to the Mesh Tools tab of the ExactFlat toolbar. And we're going to use the ExactFlat Mesh Validator. This is just going to do some very basic checks to make sure we don't have any duplicate vertices in the mesh. Checks for geometrically degenerate triangles, so that would be a triangle where that's got 0 surface area because two of the indices are coincident. Checks for topologically degenerate triangles, and that's another triangle with 0 surface area, and that's because the face actually references the same vertex twice. And it also checks for a couple other things, but in this case it's telling us that all selected meshes are valid. So at this point we are safe to proceed to the Remesher. If we did have an error reported by the mesh validator, that error would need to be fixed before we can remesh. And in fact, the adaptive remesher does use the mesh validator, and if it does detect an error or a problem, it's going to stop you and say that an error or problem was found and it needs to be fixed before you can continue. I can't show you the screen because I don't have any problems here, but it's going to offer you the ability to skip those meshes, or you can fix them automatically, in which case the mesh validator is probably just going to delete the errors. That's not the best solution because you're probably going to introduce a hole into your mesh, or you can fix manually. Again, probably the best thing to do would be to just to skip or do nothing, or not remesh at all. Skip it, close the remesher, and then you're going to want to go find and fix the error manually using our mesh repair, or the Rhino mesh repair tools. There is an FAQ video about repairing meshes, so I would recommend looking at that video and making sure that your meshes are good before you're going into the adaptive remesher. So at this point we've got valid meshes, so what we're going to do is we're going to once again cell mesh. I don't like adaptively remeshing my originals here, so what I'm going to do is I'm going to use the copy to layer command, and I'm going to create a copy of all these meshes, and I'm going to place them on the remeshed layer. That way I'm remeshing copies of the original. If the problem does occur, I've got the originals to go back to, and I don't have to waste any time creating meshes and creating my selections all over again. I can just delete the copies, I can recopy the originals, and I can start the remesher again. So now we've got same copy of the mesh on the remeshed layer, and I've also got the same mesh on the mesh layer. So we're going to switch over to the remeshed layer at this point. We're going to turn off our piece boundaries, we don't need them anymore. And once again, I'm just going to rectangle select everything. This is exactly the same as the cell mesh command. They both do the exact same thing, except cell mesh only selects meshes. Right now the only thing displayed is meshes, so I can just rectangle select and get only my meshes. So we've got all our meshes selected. We're going to go ahead and we're going to start the adaptive remesher. The best practice when using the adaptive remesher is to simply just click the start button just to get an idea for what kind of mesh is going to be created. So if there's any kind of problems that need to be fixed, we're going to see them very quickly just by clicking the start button. This also gives you a bit of an idea for where we need to go with our settings. If we need to add more triangles or improve the fidelity, then we're going to lower our tolerances, which are maximum allowed distances between the original and the new mesh. So by decreasing the maximum allowed distance, we're going to be adding additional triangles and additional vertices. Or if we need to reduce the complexity further, we can increase the desired surface tolerance, the boundary tolerance, and minimum edge length. We're going to increase the allowed distance, which is going to reduce the number of triangles and vertices. So because our input meshes are quite large, 10,000 vertices, 3,700 or 1,000, 19,000, so on, it's taking a while to do phase one, which is the analysis phase. So we finished phase one. Some of our outputs are determined to be over 1,000 estimated vertices. For the size of the parts, this is totally fine. We're just going to click yes because we want to continue, and the remesher is going to start creating the meshes for us. So because some of these pieces are very large, the back piece in particular covers the entire back of the chair. We've also got the entire front half of the skirt. These are very large pieces, so to have that high of a vertex count probably isn't a problem. They're near developable anyways, so ExactFlat, the fracture pre-flattener in particular, will probably be able to get 90% of the strain out anyways, so this isn't a big deal. If we had a mesh that had not been created through the adaptive, or a uniform remesher that had this high of a vertex count, that would probably be an issue for ExactFlat. It would probably take a long time to optimize, but because these are coming out of the remesher, ExactFlat should be able to handle them. So we're going to click OK, and we're going to have a look around here just to see where all the triangles and vertices are, and they're coming from this area right around here. So this is probably the result of some kind of meshing error that's going to have to be resolved, and we can do this a couple of ways. We can either change the remesher settings, we've got another area right up here, or probably changing the remesher settings isn't going to do it. What we're going to have to do, this probably represents an error or a problem in the mesh that we're going to have to fix, and if we switch over to our mesh layer we can see that this corresponds to this area right here. So probably what's happened is our surfaces didn't quite align 100%. So what you can do in Rhino is you can use the join edge command, and it's going to fake or force the edges to join, but you end up creating very, very tiny shelves or lips there that are then preserved through the meshing process, and the adapter remesher tries to preserve it as well. So to fix these meshing errors, usually what I do is I'll turn points on. I'll make sure that we're working with our one mesh here. So what we're going to do is we're just going to isolate this one mesh here. We'll work with this here. I'm not going to save these changes, but just to show you what's going on here. So we'll go back to Remesh. We got a problem area right here. I'm going to zoom in on it really good. So right in this area here, this is where we've got our problem. So we can see we're definitely on the boundary of two surfaces. And down here we can see that we were able to mesh it kind of all right, but as we move up here we've got very large triangles on the right next to very, very, very small triangles on the left. So probably what I would do is I would just delete all these triangles, all these quads here. So we'll do points on, and in fact I'm going to just going to zoom in. So I'm going to set, by zooming in on this one area, it's setting my target somewhere right here. And now I can rotate around to the inside. So now, if I move this, there's nothing behind it. I'm not in danger of selecting anything other than what I'm looking at here. So the easiest way to fix this kind of error is we're going to turn our points on. We can either simplify our original meshing parameters when we create the Rhino mesh. However, that's probably not going to fix this kind of issue. So instead, what I'm going to do is I'm just going to hold Alt. That way I'm not dragging anything. I'm just going to rectangle select a lot of these vertices here. So I'll try to undo. So what I want to do is I just want to be able to select our vertices here without moving the mesh. And we keep selecting the entire mesh here. So we're going to turn off mesh. Where's my mesh selection? Points, curves, surface, polysurface, meshes. There we go. So we're going to turn off mesh selection, and now we can select just the vertices here. So we're going to unselect these two here. We want to keep these two here, but we're going to select all the vertices belonging to the very, very small triangles here, and we're just going to delete them. Now we can use, we're going to turn our mesh selection back on. Now we can just use the Rhino fill mesh hole command, and we're going to fill this hole. So we've replaced probably 100 or so very, very small triangles with maybe a dozen larger triangles here, and this is going to allow the adaptive remesher to do a much better job at remeshing. So again, we're turn off our mesh selection. We're going to select all these vertices here. We want to keep these two because they belong to the big triangles, and we're just going to delete. We're going to create a big hole there. Now we're going to use the Rhino fill mesh hole command. We're going to fill this hole in. So actually I don't need meshes to be selectable to use this repair technique. So we're not going to worry about this one up here. We're just going to leave this as is. So I would repeat the process wherever we see this kind of error. So we'll go back to the adaptive remesher here. So wherever we saw that kind of error right here, so that's where we would make this kind of repair. So actually, yes, it probably would be a good idea to delete a lot of these vertices here and to just fill them in. What we're going to do instead, because if it made this kind of repair, it could take a while. I don't want to spend the whole video showing the entire repair process, but basically once we've done all those repairs, we're going to end up with meshes that look very similar to this. So this is our textured mesh here. I've gone through all the trouble of repairing these errors, and now we have meshes that look a lot better. I've also gone ahead and split the surfaces down the center here, so I'll turn our mesh selection back on. We've actually gone ahead and re-split these right down the center here. So for production, it would be better to have these splits before we do the remeshing and texturing, but this mesh was split down the center for texturing purposes. So that's why we've got these extra splitting curves back here. and that's why we've got these kind of ugly triangles right down the center. So it's best to do all your splits before remeshing. That way we've got nice meshes through the remesher process. But in this case, for texturing purposes, we had to split it again afterwards. So after you repair and remeshing, we end up with a very nice looking mesh that looks very similar to this. And we've also gone through the step of putting a texture on here. So if I change, I can either right click on the viewport title, or I can click the down arrows here, and we can change to rendered view mode, and we'll be able to see the texturing job. So at this point, we've started with a surface, we've created a mesh from the surface, we've exploded the mesh and recombined the individual meshes into logical pattern pieces, and then we've gone ahead and we've used the adaptive remesher to create meshes for flattening. And the reason we use the adaptive remesher is to both decimate the mesh and to simplify the geometry of the mesh. So when we look at this, we'll go back to shaded view. When we look at the triangles, except for the ones along this cut here, they're all mostly equilateral triangles, which is ideal for ExactFlat. So we'll go back to shaded view, and we'll go ahead and we'll flatten this mesh, textured mesh, using ExactFlat. So we've already done all the preparation work, so we've done most of the work at this point. Flattening with ExactFlat is actually a very quick process. So what we're going to do is we're going to use the ExactFlat flatten command. We're going to switch over to the Tools tab in the ExactFlat toolbar, and we're going to click the very first icon to flatten the pieces. So we can just safely rectangle select everything. This command only accepts meshes for your selection. So we're going to rectangle select everything, press enter to accept the selection, and very quickly we end up with a flat pattern. This is an initial flat pattern using one of ExactFlat's pre-flatteners. So ExactFlat is a two-stage flattener. The first stage of flattening is done with what's called pre-flatteners, so they're very fast, but they're not optimized patterns. So at this point, we're going to switch out of shaded or rendered viewport. We're going to go to shaded viewport, and this is so we can see the strain analysis on the pattern pieces. So depending on your settings, the strain analysis may be on or off. It looks like it's off, so I'm going to switch over to the highlights tab, the ExactFlat toolbar, and then click the rainbow icon here, and this is going to turn on our strain highlights. So we can see that now all our shaded pieces have rainbow colorings to them, and the colors actually represent the amount of strain on the pattern piece. So in reality, in terms of production, the more strain you have on a pattern piece, the smaller your the pattern piece is. So if we imagine our 3D model here, what I'm going to do is I'm just going to make the ExactFlat model our default layer, and I'm going to turn off the textured mesh. That way we can see the 3D reference model with strain on it. So if we imagine our 3D shape here as a rigid shell, these pattern pieces, when we stretch them or put them back onto, when we apply them to the 3D shell, the strain indicates how much we're going to have to stretch the pattern pieces to get them to fit. So the more strain we have on the pattern piece, the more we're going to have to stretch that pattern piece to get it to fit. So we've projected the strain map back to the 3D pieces. So if I were to cut this piece out here, for instance, we would have to pull it quite a bit here to get it to fit, and we'd have to pull it even more over here. So with the default legend that we have right now, red represents about 20% or more strain. So unless we're working with a spandex or something very stretchy, this material is probably going to tear, and this pattern piece is no good. But we're only looking at the results of a pre-flattener. They're very fast, and they're not optimized yet. The second stage of ExactFlat is the optimizer, and that is where we reduce the strain and sag, and we'll add additional material. We're going to relax the pattern piece so it's as close to zero strain as possible. So when we go to wrap it or apply it back to the 3D shape, it's going to fit with as little pulling or stretching as possible. So to make this easier, what we're going to do is we're going to minimize our perspective viewport, and we're going to maximize our top-down viewport. So we're looking straight down at our pattern piece. We're also going to make the pattern layer the default layer, and we're going to turn off the model layer. So we're only looking at the 2D pattern pieces now. So our first step from here, when we look at this pattern piece, we see that we've got a lot of strain. We also see that we've got flip triangles on here, and we can tell this by the cross marks here. And if we actually zoom in, we'll see that all the triangles actually have inset triangles on them as well, indicating which triangles have problems. So in reality, the flip triangles, these represent folds or wrinkles on the pattern piece. So conceptually in the mathematical model, this pattern piece is folded in under itself or on top of itself. So again, these are patterning errors. They need to be fixed, and the easiest way to fix them is to just run a different pre-flattener. And we do have a video on various techniques for removing flip triangles. So if you have questions about that, I would recommend checking out the video. It talks about all the different methods for removing flip triangles. So for us, we're going to switch back to the Tools tab of the ExactFlat toolbar, and we're just going to use a different pre-flattener. So for this pattern, I'm going to start with fracture. And with fracture, we get a different pattern for each starting, or depending on the edge of the mesh that we select, we get a different pattern. Because fracture works very well on developable surfaces, we like to choose vertices along a plane of symmetry. So I'm going to click a vertex somewhere along the center line here. And when I do this, we get a pattern piece. In this case, we've got a very nice pattern piece that has very low strain. However, we still have one flip triangle up here. But because I like the shape of this pattern piece so much, I'm going to accept this, and we're going to try a different tool to remove this last flip triangle up there. So for this one over here, we'll pick a couple different locations. We're not getting rid of the last flip triangles, so we'll try the flip triangle removal tool to finish off these pieces here. We're going to repeat the process for the rest of the pieces here. So for all of these, we're getting quite a few flip triangles here. So maybe I'm going to switch over to our Pelt algorithm instead. In this case, we're still getting a good starting shape, but we're eliminating the flip triangles. So we'll try Pelt on these ones here. And the shape is still good. We got a bit more strain. That's okay, it just means the piece has shrunk a little bit compared to fracture, but the optimizer is going to deal with that for us. So we'll just go ahead and we'll repelt the rest of these here. And the biggest goal here is we're first and foremost removing folds and wrinkles or flip triangles. And secondly, we're trying to change all the colors or reduce the strain from high strain levels to as close to 0 as possible. So the default legend in ExactFlat, 0 indicates no strain or sag. Cyan, the blue color here, represents 5% strain or sag. Green is 10%. Yellow, we can see a bit of yellow right around here, is about 15%. And red is 20% or more. So when our pattern pieces turn more white, that's indicating that we've got a good pattern with minimal strain or sag. So at this point, we've flattened our pieces. We've used the Pelt tool to remove the flip triangles and most of the strain and sag. So what we're going to do now is we're going to use the Optimize and Spring tool here, and this is the second stage of ExactFlat, and this is where we optimize our pattern pieces to the best fit possible. So we're just going to select all our pieces here, and we're going to go ahead and we're going to optimize these pieces. So we're just going to use the default settings, and we're going to go ahead and hit OK, and optimize this for a cotton material. If you are working with a different material, ExactFlat does come standard with about 85 different materials, and we do partner up with University. I believe the cost is about $25 US. They require about a 1 foot by 1 foot swatch of material, and usually within one business week they'll be able to analyze and test your material and give you back a report that you can then use to form your own mathematical model of that material for use in ExactFlat. So we do have a material manager that you can add your own materials to ExactFlat, but by default ExactFlat comes with about 85 different materials. So for this chair we're just going to use a cotton. We're going to go ahead and click OK and start the optimization process. So the optimization process always starts off with a quick initialization phase, and that's where ExactFlat's going to analyze the pattern piece and build a table of values that are referenced over and over again. Once that's done, we're going to start optimizing, and we can see as it's optimizing, Not so much right now because we've already removed most of the strain, but the shape is going to change as it's optimizing, and the colors are going to change to represent the level of strain as the piece is optimizing as well. So as expected, we can see that the color for this piece has shifted almost predominantly to white, and this makes sense because the back of the chair is more or less a developable surface. We do have some color around the edges, and that's because the edges were filleted for this model, so we do have some double curvature around the edges, but mostly we don't have much strain or strain on the pattern piece at all. We do see a bit of gray or darkening around the center here, and this represents sag or an excess of material on the pattern. And when we go to fit this back onto the chair, this may manifest itself. So this piece is optimizing now. We can see that the shape has changed. It's expanding slightly, and the colors are being reduced. But the sag here, this may manifest itself as wrinkling or puckering on the material. It just may not be as tight as everywhere else. So depending on your project and what you're working with, that may or may not be acceptable. We do have some other tools that can be used to reduce the excess material as well. Our global target strain tool being one of them. So that one can actually be used to intentionally reintroduce a bit of strain into the pattern. So if you need to have a tight fit, you want to make sure that you're always pulling the material. Global target strain is a very good way of ensuring that you always have strain on the pattern, and you can configure the amount of strain with the tool as well. So we're going to proceed on through the list. We're going to optimize all these pattern pieces, and we're going to reduce all the strain and sag. So as we're optimizing, we're going to see the colors are changing on all of them, and the shape is changing as well. So as these pieces are optimizing, we can see that the different values and the status report are changing. So the most important values that we're going to be looking at are probably the average energy density. This is telling us the overall average amount of energy or strain in the pattern piece. So the higher this value, the more strain we have. So as it optimizes, we're going to see the average energy density. It's always going to decrease. It's never going to go up. It's always going to decrease, and this represents the progress of the optimizer. A couple of related values are the minimum energy density. So this is the smallest amount of energy found on the pattern, and the other one is also the maximum energy density. So we've got a very, very high maximum energy density for this piece, and this is always going to generally it trends to the trend is for this to reduce as we optimize, but some pattern pieces we're always going to get anomalous values, and that just may represent a very awkward portion of the pattern, or even an error on the model that was not caught through the previous methods. But generally speaking, this usually trends downwards, although it is always going to spike up and down as different iterations are tried. But this is usually the maximum local energy on the pattern piece. In this case, we got quite a bit here. So there probably is a small error somewhere on the pattern, or a very, very awkward tight corner that you may want to put a dart in to relieve some of this energy. We also are going to look at the no seam stretch error. So the no seam stretch error is simply the difference in perimeter length between the corresponding piece in 3D and the 2D pattern piece. So this is going to give you a bit of an indication for how well your pattern is going to fit. So when we look at the no seam stretch error, we've got a difference of, for this piece right here, we've got a difference of about 44 millimeters, and when we consider the entire boundary length of about 2100 millimeters, 44 millimeters is fairly small. So that's not a huge error at all. That's about 4% error. And this number is also going to reduce as we optimize the pattern piece. So generally speaking, the closer to zero this difference is, the better the fit. And this is important, especially for manufacturing and sewing the pattern pieces. So if you have two pieces that sew together, When the no seam stretch error is 0 or very, very small, this is a very good indicator that our sewn edge lengths are going to be the same. So we're going to have the same length of material on the right hand side of our seam as we do on the left hand side of the seam. So we also have a couple settings in when we started our optimization. We didn't change any of the settings, but one of the settings there is our preserve boundaries option, and this will help minimize the no seam stretch error, and that option is especially useful when working with very rigid materials such as leather, or even if we're working with like metallics like aluminum or steel. They don't stretch when working with them, so it's important that the boundary lengths do not change. We'd rather have the piece be a little bit too small. We can always deform the piece to make it fit, so long as the edges are the same for welding and assembly. So at this point, we finished our optimization, and we can see that for all the pieces, the color has changed. We've reduced the color from reds and yellows all the way down to predominantly white. And we do see a bit of green in some of these pieces here, but this is just the way the pattern piece was created. So at this point, we've got a pattern that it's kind of difficult to tell how this fits back together. So what we're going to do is we're going to start with a piece that we know it's very identifiable. We know where it goes. So we're going to start with this piece right here. This is the top of the seat where the cushion goes, and we know that this part here on the right is the front. So what we're going to do is we're going to use a Rhino tool. First, actually, I'm going to switch over to my highlights tab and turn on our edge highlights so we can see the triangulation. And now we're going to use the Rhino rotate tool, and I'm going to rotate this piece here. And what I'm going to do is I'm just going to choose our two vertices right on the edge here, and we're just going to rotate this so it's perfectly horizontal right to left. And this is going to serve as our anchor or our base. And now what I'm going to do is I'm going to use the ExactFlat find tool. I'm going to change my offset. Right now it's 10 millimeters or 1 centimeter. We're going to change this to just to make it easier for us to work with, we're going to change this to about 30 centimeters. And now what the find tool does is as I select one edge, it's going to find the neighboring pattern piece. So as I move my cursor along here, we can see the neighboring pattern piece is being highlighted down here. So as I move my piece, if we look back over to the other piece, we can see that the neighboring edge is being highlighted as well. So I'm just going to select one piece here, and that neighboring piece is going to snap over to my selection points. So I think 300 millimeters is probably too much. We'll change this to 10 centimeters or 100 millimeters. We'll do it again, and we get a much more reasonable distance here. So I'm going to repeat this process, and what we're going to do is we're going to basically just rebuild our pattern and make it a little easier to do the patterning work. So very quickly we've been able to rebuild our pattern and move all our pieces together so we can very easily see how this chair now assembles. So our model that we started with was a 3D textured model, but so far we've only been working with shaded models. So at this point what I'll do is I'm going to right click top up here, and we're going to go back to rendered, and we can see that our 2D pattern is in fact still rendered. So we have our texture, we've preserved our texturing all the way through the flattening process, and we can verify this. So what I'll do is I'm going to again use our find tool. This time I'm going to set my offset to 0. I don't want any offset. And if I just select a piece right here, we've got part of a flower on one side, and if I find the piece over there, we can see the texture flows between pieces. So we've preserved our texturing all the way through the flattening process. So I'll set our offset back to 100, and I'll just move this piece back to where it was. So at this point, depending on your workflow, we can do different things. We can save the file, and by saving the file that has a flattening project, we're saving the work with flattening projects, so we can save this file as a Rhino 3DM, and we can come back to it at any time and continue flattening. We can also use the the ExactFlat export command to create a DXF. So the DXF is going to contain seam line, so that's the natural perimeter of the pattern piece. It's also going to contain an optional seam allowance, a global seam allowance. So for sending this file directly to a cutting table, we might want to add an optional seam allowance for cutting, or if we're going to be importing this into something like Gerber AccuMark, we may want to turn the seam allowance off and then create our seams using AccuMark or some other patterning tool. We can also manually add our notches and tags to the pattern piece. So in this case, if we want to add notches, we can use the notch tag dialog. And from here, I can manually add notches. So I'm going to add a series of slit notches here with my tag the way I've configured the defaults. Whenever we use the %n, it's going to add a unique auto-incrementing number. So my tags are going to be comprised simply of numbers here, and all my tags that I add are going to be red. So I'm going to click the Add button, and I'm going to start adding some tags along the edge here. So as I add tags to one side, we can see that they're automatically appearing on the right-hand side, and it's a little difficult to see because of the shading. So what I'm going to do, I'm going to switch back to shaded, and now we can get much better contrast with the gray. So again, I'm going to select vertex right here, and it's adding a notch right there as well as on the neighboring side. So once we're done adding all our notches, we can go ahead and we can either create a DXF file, or if we're going to be printing these, in this case it's a chair that's being sent to a combination printer, plotter, and cutter. So in this case we're going to use ExactFlat Monarch, and we're going to render these pieces, and we're going to save them as a PDF file that combines both our print information and our cut information. So to do this, it appears my Monarch toolbar is missing. The plugin is loaded though, and the command is Monarch Render. So we're going to type in Monarch Render, and we're going to select our pattern pieces here, and we're going to go ahead and we're going to render these. So we've got all our objects here selected. We're going to render these at 150 dpi. The resolution that you're printing on is going to depend entirely on your printer and the material you're working with. For something like a cotton, depending on your cotton, usually anything over 100, 150 dpi, the ink just tends to start to bleed, so you don't need very, very high resolution when printing onto materials. But again, this depends entirely on the material you're printing onto, so it's best to do some tests to figure out what the optimal resolution is. For this, we're going to render at 150 dpi. We're not going to do any kind of conversion to the texture. This is a preview of what the texture looks like, but we do have options for converting to grayscale and black and white depending on your use of Monarch. But for this case, we're not going to do any kind of conversion. And we're going to, when we do this rendering, we're going to create a PDF. We do have the option to render to PNG as well as TIFF, but for this case we're going to render to a PDF so we can combine both printing information with cutting information. So we're going to put the rendering onto a print layer, we're going to put our cut line onto the cut layer, we're going to put our seam line onto the seam layer, we're going to turn off the grain line for now. We're going to put, we don't have any marking points or marking lines, we haven't traced anything onto the chair, so we're going to turn those off. We don't have any V notches, but we do have slit notches, so we are going to create, we can add both notch points or notch lines. In this case we're going to add the actual lines of the geometry, and we're going to change the layer name to simply notch. And we're going to put our tags, so that's the auto increment text, we're going to put that onto the tags layer. So we've already selected a location to render to. So at this point we're just going to go ahead and we're going to click the render button. So it's not going to take long for ExactFlat to render them. This piece here is about 28 by 41 inches, and we can see the previews appearing in the pattern viewport as we render it. And if we go to our folder, we can see the PDFs are starting to appear. So for this piece here, we did add our notches along the perimeter. So if we zoom in, we'll walk the perimeter here, and we should be able to see our notches along the perimeter. I think maybe I forgot to check that off, so what we'll do is we'll go ahead and we'll re-render those. Monarch render, delete all of these. And we'll rectangle select our pattern pieces. We're going to render these, we'll keep it at 150 dpi, no conversion, and yeah, we do have notches on, so we'll go ahead and we'll render again. This is a different piece. So the piece labeling does depend on the order that they are selected. So we've got our piece here, and if we zoom in, we can see that we've got our notches and our labels created here. So I'll expand the layers tab of the PDF here, so we can see we've got a print layer, and if we turn that off, our print disappears. We've also got our cut layer. So I turn this off, our internal blue line, or sorry, our external red line is going to disappear. We've got our seam layer, so this is going to be the internal blue line, so that's going to be what we sew to. We've also got our notches and our tags layer, so if I turn off the tags, the number 5 is going to disappear. And we can see our notch right there, and that is also on a separate layer, so if we turn that off, our notches disappear. So depending on your workflow, you may want to create a DXF of your pattern. You may want to render it as a PDF or something else. But using this workflow, we can take any mesh or surface data, whether it has a texture or not, and we can very easily create 2D patterns out of it and flatten it. Thank you for watching.